There's a little demo I forgot to do for you the other day on Boyle's Law. I want to show you something. What I've got here is just a large Erlenmeyer flask, but it's not just an Erlenmeyer flask. It's a little thicker walls, and it's got this little nozzle coming out of it. I put a stopper on it so it's airtight. And coming out of that nozzle, I have a hose. Okay? If you look at that little nozzle here, coming out of that, there's a hose. Now, the hose is connected to the sink over here. Okay? And this nozzle here is kind of weird. You've seen these kind that are just like pyramid shaped, and you turn them on, water comes out too fast. I tell you not to use them. They're for hoses. But this was special because it has a little side hose here, a little side nozzle. So what happens is the water goes by this way, okay, and that creates a lower pressure, which creates a suction or a vacuum, pulling along this hose and therefore decreasing the pressure inside here. So let's watch what happens to the syringe I've got in there. All right, if you can see that pretty well, hopefully on the camera as well, if you guys can see it. Turn that on. Watch the syringe carefully. What's it doing? Can you see that? It's actually increasing its volume, isn't it? Quite a bit. Like almost double. What does that mean must be happening to the pressure in here? It's got to be decreasing, right? Because that's what law? What law is that? Now watch, when I let the air back in, the syringe will go back to where it was. Slowly, but it does. All right. So basically, that's just another example of Boyle's Law. I decrease the pressure, and I increase the volume of the syringe. I let the air back in, and it got smaller. All right. Where we use that, by the way, is something called a Buchner funnel. Okay, I can actually have this thing here. It's a funnel that sticks into one of those things. And the reason I would use that is it would actually, if I want to filter something, remember we filtered this a couple of times, and it takes a long time to wait. So if I have this like this, and I hook this up, and there's suction pulling it down, all right, what's going to happen? It'll happen a lot faster. It'll suck the water through a lot quicker. All right, good enough. Now, that was just something I forgot to show you yesterday. Now, for today, I got something pretty cool. Okay? We're going to do our next gas law today. I'm going to need this thing. Fill up with water again.
Are we noting?
Just watch. Yes, we are. Watch this first. Now, notice I've got some soda can here. And in there, so you can all see it. All right, and just a bottle of water. Now, I open the can's open. I put it on the burner here, and I'm gonna look for my. There you are. All right, I have a little bit of water in there, and I'm boiling that water right now. Now, watch what I do here. You watch it carefully. Everybody, pay attention here. I'm gonna take that can, and I'm gonna put them into this cold water.
Oh.
Scared the crap out of me. Yes. What the heck happened? Well, yesterday we talked about, just a second ago, pressure and volume, right? What am I talking about today? What did I do to the can? Up here. I heated it up, right? And then I put it in cold water, right? So it's not going to be volume and pressure. It's going to be volume and temperature. Sure. And that's Charles' Law. Okay, that's what Charles' Law is all about. Turn that light off and look up here. That's what Charles' Law is. I want to explain to you what went on there, too, and why I did that. Okay. Good enough. Charles' Law. And you guys, Marvis, how long have you been doing the lights for me?
Since the first day.
What's the normal way the lights look right now? There you go. There you go.
I like it the other way.
Yeah.
No, I'm not.
You see, the other way, the light's over the board and you can't see it as well. All right. And then there's no light over you where you're trying to write, so that doesn't make any sense. All right. Charles' law simply says the relationship, it talks about the relationship between volume of this can and the temperature of the gas in the can. As you saw, when I cooled it down, when I lowered the temperature, I turned it upside down in the cold water, the volume of the can shrunk. Okay? So I lowered the temperature and I lowered the volume. Okay? Yesterday, with the pressure, it was the opposite. What do we call that proportion yesterday for the volume and pressure one? Inversely. What do you think this one is? Directly. And the same thing's true about heating something up. If I heat up, would I want to put a soda can on here and heat it up if it hadn't been opened yet? What's it going to do? It's going to blow up. It's going to expand to the point where it's going to blow up. You never heat a closed container. So that's what Charles' law says. Volume and temperature are directly proportional. The temperature has to be in Kelvin, though. Volume and temperature are directly proportional. What is it that crushed this can?
Pressure.
What pressure? The water pressure of the water I put it in? No. What? Air pressure in the room. Remember that big metal spike I had here yesterday? How heavy that was? That's how much pressure is on every square inch of your body. That's how much pressure on every square inch of this can. When I turned this upside down, I sealed the top because it was now underwater. So all that pressure, as that inside the cooled off, the gas cooled off, it was no longer the same as the pressure outside. All right, it just crushes that can. There's enough pressure here to crush more than this can. All right, believe it or not. You don't realize it because our pressure is about the same. But I've seen the same demo done. Bill Nye, you guys are big Bill Nye fans. He took a big oil drum, like I don't know, 60-gallon, 50-gallon, I don't know how much they are, but you know what I'm talking about. Big oil drum. Put it on with a crane. He put it on a barbecue grill with some water in the bottom. Heated it up, put a top on it, and threw it in a swimming pool. Guess what? This big steel drum crushed like an aluminum can. Just crushed it because that's how much weight, that's how much pressure there is in the air. All right now. You just can't feel it because your pressure inside is about the same. All right, but again, we're not talking about pressure this time. We're talking about volume and temperature. So temperature and volume, unlike Boyle's law, which looked like this. Here was Boyle's law. V2 P2 equals V1 P1. Do you think this law is going to be V2 T2 equals V1 T1? Would that make sense? Why can't it be that? Because this was inversely proportional, right? And we know temperature's not inversely proportional, right? What do you think it might be? What do you think the formula for this guy might be?
V2.
Exactly. V2 over T2 equals V1 over T1. By the way, you might be wondering why I'm writing this way, because there are multiple ways I can write these equations. I could have had it T2 over V2 equals T1 over V1. I could have had it V2 T1 equals T2 V1. I mean, I could write it a bunch of different ways. The reason I always write it this way, and a lot of times they're in books written this way, notice V2 is on the left side in the numerator. That's useful because most of the time when we're solving gas law problems, here's what you're solving for. Hey, what will happen to the new volume? That's your variable. If I do this to the temperature, if I do this to the pressure. So that's why it's set up that way, to make it easier for you to rearrange the equation most of the time. Anyway, there it is. That's the equation, and that's the end of your notes. I'm going to do two examples, and you'll find that in the second example especially, this one can get a little bit harder, at least when it comes to the math, when it comes to the algebra. All right? But let's do these two examples. They're not very difficult. I will check your homework today. We'll pass that up in a little bit, but let's get through this first. You guys all did the lab yesterday, right?
Yeah.
With the exception of Patty, who wasn't here. All right. What volume will 700 milliliters of a gas at 20 degrees Celsius occupy if the temperature is changed to 266 Kelvin? You're going to solve all of these the same way. And I need to see this work. I just checked the homework from the last period, and there were a lot of grades that were not 10s. They were not 10s because they had just the answers or a couple of numbers written down. I want to see the work. pick the numbers out of the equation, show me the formula, rearrange it, and plug the numbers in. You may think right now that I don't need to do that. I can just grab my calculator and do it. All right, that may be true for some of the easier ones. It is not going to be true for the harder ones we're going to get to. All right, let's do this guy. This next one in particular, probably couldn't just plug into the calculator. There's too many things to do. V1, V2, T1, T2. You write them down to the side, you pick them out of the problem. The question says, V1 is what? What's your initial volume? A lot of numbers up there. Which one's the volume?
700 milliliters.
Everybody agree? 700 milliliters? It says, what volume will 700 milliliters occupy in the future? You got to be able to read. And so what it used to be is 700. What it's going to be is V2. What volume will it occupy? It's asking you that. That's your unknown. You also know that's the volume because it's in milliliters. Milliliters are a unit of volume. T1. What's my initial temperature? You have to read. You have to understand English. Jared.
20 degrees Celsius.
Exactly. And what's my T2? The only number left, really, 266 Kelvin. Now, obviously, I have a problem here with my units, but I don't have a choice this time. You know, in the last time I did one of these metric conversions, and when I do another one next example problem, I could say, well, you can convert this guy to that, and that guy to that. It doesn't make any difference. It does this time. It has to be in Kelvin. You know what? Even if both of these guys were in Celsius, I would have to convert them both to Kelvin. So why? What's the difference? Here's the difference. Okay. Celsius has a 0 and negative numbers right in the middle of its scale. It has a 0. That's not good. If I throw a 0 into a temperature up here, what kind of number am I going to get? Well, no, I won't get an unreal number, right? It's not even going to be, you can't divide by 0, right? So I can't do that. It's not proportional using Celsius. I've got to use Kelvin because Kelvin 0 is absolute 0. You can't reach it, all right? And there's no negative Kelvins. All right, so I write the equation down next. Oh, I said I was going to do it, then I didn't do it. So I have to convert Celsius to Kelvin. How do I convert Celsius to Kelvin? I add 273, and I get 293 Kelvin. Correct? 293. All right. Now I write the equation down. V2 over T2 equals V1 over T1. I rearrange it. How will I rearrange this guy? And I need you to see. I need to see this. Look at if every problem's the same in the homework, and you just write the equation once and then write the numbers in for each one, I don't care. But on a test, every single problem better have the equation rearranged and the numbers plugged in. Okay, can't just have the answer. All right. So what do I got to do to both sides to rearrange this guy? I want to get V2 by himself. Do be careful here. I get some mistake. It shouldn't happen, but I do get a mistake at this point. What do I do to both sides? What do you think?
Multiply by T2.
Multiply by T2. You know why I get a mistake there? Because a lot of people want to say, well, you're going to divide. Whenever you want to get rid of something, you always have to divide. No, you don't. If he's in the denominator, I don't have to divide by T2. I have to multiply because that's when he'll cancel out there. And then I'll get V2 equals V1 T2 over T1. Right? Everybody look good with that? Plug my numbers in. V1 is 700 milliliters. T2 is 266 Kelvin. And T1 is 293 Kelvin. Get your calculator out. What does V2 come out to be?
635 milliliters.
635. And Kelvin cancels, leaves you with milliliters. Good. Very good. And that one's not too bad. By the way, I did say you can go back when you're done and double check if it makes sense. Let's see if I put 635 here, does that make sense? Let's take a look. Well, the temperature went from 293 down a little bit to 266. I should expect the volume to go down a little bit. Temperature, the volume was 700, went down to 635. It makes sense. Am I sure it's exactly right? No, but if it had gone up, I'd be wrong. All right, I know that. Okay, good. There's your first one. Now the second one is going to have a little bit more difficult math, but I'm going to show you a trick to make it less difficult. Copy that guy down, and we'll do him on the board.
you know, I don't care that this one is going to end up being a little bit more difficult. It also has more conversions in it. I'm still showing the same 3 basic steps. V1, V2, T1, T2. What's my initial volume here, people? Read it. Marcus, what do you think?
24.1 liters.
Good. Okay. Ellie, what's my V2?
$9.65.
965 milliliters. Good. It's compressing it to 965. Okay. What's my initial temperature?
-40.
Negative 40 degrees Celsius. And my new temperature?
Question mark.
Exactly. Determine the new temperature. All right. Good enough. But I got lots of problems with this one, don't I? I got milliliters and liters. I got to change those. It does not matter which way you do these. Milliliters, I can convert this guy to milliliters. I can convert this guy to liters. I'll convert this guy to liters. Milliliters on the bottom, liters on the top. 1 liter contains 1,000 milliliters. I get, dividing by 1,000, I'm going to get 3 spaces, 0.965, making it smaller because I'm dividing liters. I also have 40 degrees Celsius. That's a problem. I have to add 273. And I specifically gave you a negative 40 degrees Celsius, which means you've got to be careful of that too. It's not going to be 300 and something. It's going to be what? 233 Kelvin. Good. Okay, because you have a negative 40. That's 233 Kelvin. Good. All right. I've taken care of that. That's all the first step. Second step. This is the one I want to spend a little bit of time on this time. V2 over T2 equals V1 over T1. What's the problem with this? The same problem we had when you were solving density problems and you had to solve for volume. What's the problem with this guy? That people make mistakes trying to rearrange it. Where's the variable I'm looking for? He's in the denominator. Now, some of you may not realize, but that's a problem. Because if I ask you, what do I have to do to both sides to get T2 by himself? That's what I'm looking for. A lot of people will say, I'm going to divide by T2, or I'm going to multiply by T2, or I'm going to divide by, by V2, or multiply by V2. That will not work. You cannot multiply or divide by V2 and say, okay, now I got T2 by himself. I actually have to do it in 2 steps. Okay? If I were to use just the basic rules of algebra, here's what I would have to do. But I am going to show you a trick where you won't have to do this every time. Okay? Basic rules of algebra says I got to get him out of the denominator first. So I'll multiply both sides by T2. And I'll get, don't do this, I just want you to watch. I get V2 equals V1 T2 over T1. And then I'd have to do what to both sides? I multiply by T1 over V1. So your final answer would be V2 T1 over V1, because these guys would cancel. Oops, these guys would cancel. Leave you with T2 would equal T1 V2 over V1. All right? But that's a pain in the neck. Don't want to have to do that. Can somebody think of, and probably most of you do this, an easier way? Let me erase all this and see. We can do this an easier way. Let's start with my equation again. Here's my equation. V2 over, oops, sorry. V2 over T2 equals V1 over T1. What can I do that would be a lot easier than having to go through that? What would you do?
Cross multiply.
Yeah, most people like to cross multiply, and that's fine. If I cross multiply knowing I'm solving for T2, I'd have T2 V1 equals V2 T1. Now it's easy. What do I do to both sides now to get T2 by himself? Divide by V1, and notice it's the exact same equation I just derived a minute ago. But there's another way I could do it. Watch this. Watch this. Say I have V2 over T2 equals V1 over T1. This is a reciprocal. This is a proportion, and I can take the reciprocal of both sides, and it's still the same proportion. So that equation could just as easily have been written T2 over V2 equals T1 over V1, couldn't it? Why is that easy to rearrange? Because now the T2 is already in the numerator. So all I would have to do is multiply both sides by V2. And again, notice I get the exact same equation. I don't care. Here's my point. I don't care how you get it. I don't care if you use step-by-step rules of algebra to get it. I don't care if you cross-multiply to get it. I don't care if you flip them upside down and take the reciprocal of both sides to get it. But eventually, I want to see the equation, okay? Which is what? T1 V2 over V1, right? And then you got to plug your numbers in. T1 is 233 Kelvin. V2 is 0.965 liters. And V1 is 24.1 liters. Get your calculator out, plug those guys in, and see what you get. Who had an answer? It's going to be a very small number, I believe. What'd you get? Anybody?
.00933.
No, it's not that small.
I got 9.3.
No, I'll tell you what he did. I'm glad to see somebody get 9.3, 32, 33.
I don't think the other three typed in. I think I just
No, I know what you did. When you looked up here for your values, I've done this myself. You looked at this one, you plugged that one in, you plugged that one in, and you plugged that one in. In other words, you didn't look at the actual conversion, I'll bet you, because
I
maybe
still
you
put in
did.
the 965. I think I just did 23 or something.
Okay. All right. Because you're off by exactly 3 decimal places, which would make sense if you're off by 3 decimal places this way. See what I'm saying? That's why I thought. But either way, that is a possibility. Just looking over here, plugging them, which is why. How many points is that going to cost him? 1. And I don't care how long this problem gets. This problem right here would be worth quite a few points. Why? Because you had to do this conversion. You had to do that conversion. You had to do a harder algebra problem, and then you had to actually do the math for it. But it's only going to cost him 1 point if he showed me all this work and then accidentally, when he got his calculator out, plug that number in instead of that one. It happens. Everybody does that. Okay? So it won't cost you so many points.